We'll continue with section 10.2, talking about graphing equations in polar coordinates. We'll start with a couple of basic equations with their graphs, and then we'll also talk about how we can kind of use some knowledge along with some help from our calculator to do the same thing. So, certain types of graphs are particularly convenient to represent in polar coordinates. In particular, lines through the origin, and then as we're going to see in a minute, circles, are very nice equations in polar coordinates. We're going to start with our lines through the origin. The equation y equals mx, right, is just a line with slope m and a y-intercept of 0, so it goes through the origin. If I'd like to convert this to polar coordinates, let's start by dividing the x over to the left-hand side. And then if you remember, this is one of our conversion equations, right? Y over x is the same as tangent theta. So what this says is the tangent of theta is equal to the slope, or just some constant. Well, that means that the theta would be the inverse tangent of that constant, which again is a constant. So if you have theta equals some constant, that is a line through the origin. If you think about that one, it kind of makes sense. If I just sort of randomly draw a line through the origin here, is it not true that all the points on this line have the same theta value? They've all been rotated the same amount from the positive x-axis. This half of the line would have r values greater than 0, positive r's, and this half of the line would have negative r's. So, let's use that idea to graph a couple of equations. If I have the equation theta equals pi thirds, that's simply going to be a line through the origin at an angle of pi thirds, or since my graph paper is marked in pi twelfths, I could think of it as theta equals 4 pi over 12. 1, 2, 3, 4, that would be right here. And so I'm simply going to draw that line through the origin. Our second equation, theta equals negative pi over 4. Again, it's going to be a line through the origin. That would be negative 3 pi over 12. So that's going to go, let's see, negative 1, 2, 3 right here. And if I draw that line through the origin, it'll look like that. And there's my theta equals minus pi over 4. So, fairly easy to deal with, lines through the origin. The next type of equation that's quite easy to deal with are circles. If we have a circle centered at the origin, we've seen these equations before, right? In rectangular coordinates, the equation of a circle is just x squared plus y squared equals some constant squared. And again, using what we know now about our polar rectangular conversion equations, x squared plus y squared is just r squared. So that says r squared equals a squared, or r equals technically plus or minus a, In other words, r equals some constant. Is going to be the equation of a circle in polar coordinates. Again, does this make sense? Sure. If you just think of a circle, some random circle centered at the origin, at every single point on that circle, we are exactly the same distance from the pole, right? If that's the A value, then at a point over here, my distance from the pole is that same A value. And that's going to be true no matter where I look on my circle. So the distance from the pole, r, is always constant for a circle. So again, graphing equations that look like r equals a constant, pretty simple in polar coordinates. If I want to graph r equals 2, that's just going to be a circle of radius 2. And if I want to graph r equal 4, that's just going to be a circle of radius 4. So graphing circles and equations of circles, really straightforward in polar coordinates. All right, let's look next at doing some converting between polar and rectangular equations. Sometimes, not always, but sometimes it's possible to convert an equation that's given in polar form to an equation in rectangular form that we can recognize. To do this, we'll be using a little algebra, a bit of creativity, and we'll also make liberal use of these conversion equations that we studied before. Okay? Converting each polar equation to rectangular form, and then hopefully recognizing it well enough to sketch the graph. My first equation, r cosine theta equals 1. I'll make use of my conversion equation and recognize the left-hand side as just x. So this is the equation x equals 1, which I certainly recognize in rectangular coordinates as simply a vertical line. And so the graph would simply look like that. All right, well that was really nice, right? If I have either an r cos theta or an r sine theta in my equation, I can immediately replace them with either x or y. Unfortunately, in B, I don't have that, right? I have r equals sine theta, and I sure wish there was an r in front of that sine theta, because if there were, I'd be able to replace it by y. Well, a little algebra, and I can get one there, right? What if we just multiply both sides of this equation by r? This is now r squared equals r sine theta. Even better, I know what r squared is. It's one of my conversion equations. It's x squared plus y squared. And r sine theta, that's y. So I've got the equation in rectangular form, x's and y's instead of r's and thetas. I still don't maybe quite have it in a form that's easy to graph yet. I can start to see this is going to be the equation of a circle, but I got to deal with that y over there. So I'm going to subtract the y over, getting 0 on this side. And then to finish this off, I'm going to need to complete the square. See, half of 1 would be 1/2. Squared would be 1/4. So I'll add a 4th on both sides. So my equation is now x squared plus y minus a half, all squared, equals a fourth. What is that? That is a circle. The center would have x still 0, but y would be 1/2. And that's r squared, so the radius would be the square root of a fourth, or 1/2. So my center is at 0, 1/2, and the radius is a half. So if I go a half in each direction from the center, that will give me my circle. All right, we've got one more example of going from polar to rectangular down here. I start with r equals secant theta, tangent theta. First of all, I don't have any conversion equations with secant in them. So I'm going to start right out by using a trig identity. Secant theta is the reciprocal of cosine theta. Kind of liking that, because if I multiply the cosine theta over, I'm going to have r cosine theta, which I like. That's x. So let's do that. Let's multiply both sides of this by cosine theta. Cancel it on this side. So I now have r cos theta equals tangent theta. All right, r cosine theta, that's just x. And tangent theta, again, if you look at those equations at the top of the page, is y over x. Well, now if I just multiply the x over, I've got y equals x squared. That is simply a parabola. Looking like that. Right? So again, bit of algebra, be a little creative, try and convert what you were given to something that looks like those conversion equations at the top of the page. That's what's usually going to work out best. All right, let's go the other way. These were given in polar coordinates, and we wanted rectangular. What if I'm given rectangular coordinates, and I want polar? We'll continue to use those same conversion equations, right? The same four equations that were at the top of the previous page. We'll continue to make use of these, so keep those in mind all the time. And the first equation that I would like to convert to polar is y equals 2x minus 1. Notice here in the polar equation, we'll consider it finished if it's either solved for r or solved for r squared. All right, usually the simplest, most straightforward thing I can do with these is to literally replace y with r sine theta and x with r cosine theta. So that's what I'll do here. That'll give me r sine theta equals 2r cosine theta minus 1. If I'm going to solve for r, I will definitely need to, at the very least, get all of the r's on the same side of the equation. So let's see, just to keep the 1, maybe make it positive, I'll put the 1 on this side and bring the r sine theta over to the right-hand side. I can now factor the r out over here on the right. And then it's fairly easy to solve for r just by dividing by all that stuff. And again, this would be considered finished because it is solved for r. Notice, by the way, how much more complicated the equation of a line is in polar coordinates when it doesn't go through the origin. When it did go through the origin, it was just theta equals a constant, right? When it doesn't, significantly more complicated form. All right, let's try B. I'm going to do the same thing here. I'm going to replace the x with r cosine theta and the y with r sine theta. That would be r squared cos squared theta minus r squared sine squared theta. And I'm going to factor out the r squared. And then divide to get r squared by itself. Okay. That is solved for r squared, so to some extent it would be considered done. But if you do problems like this, like the exercises in your book, things like that, you're going to find that typically when a trig identity can be used to make the solution look simpler, they'll usually do it. That looks a little familiar to me. So I might consider looking at my list of trig identities. And notice there it is right there. Cos squared theta minus sine squared theta is cosine 2 theta, which is a lot simpler looking. So in all likelihood, this would be rewritten as 1 over cosine 2 theta. But now there's another trig identity. The reciprocal of cosine is secant. So I might write r squared equals secant 2 theta. And that now is a nice simple equation for that rectangular one. There's the polar form. All right, let's do one more. xy equals 4. Same deal. I'm going to replace x with r cos theta and y with r sine theta. Gives me r squared cos theta sine theta equals 4. And I'll solve for r squared by dividing by the cos theta sine theta. Not terrible, but I might again ask, is there a way I could make that look simpler? Cosine theta times sine theta. If I look at my list of trig identities, I'm almost there. Here, with the sine 2 theta, except I would need a multiplier of 2 in front of my sine theta cos theta. Well, that's not real hard to get. Right? This is a fraction, so I can multiply by the form of 1, 2 over 2, and make that 8 over 2 cos theta sine theta. And now that denominator works perfectly for that identity, sine 2 theta. One more thing, the reciprocal of sine is cosecant. So I might write this as r squared equals 8 times cosecant 2 theta. And that's about the simplest I can make that one. So a bit of playing around with some trig identities sometimes to get answers to match the back of your book. I'll encourage you to do the best you can with these. I'm not necessarily going to penalize you heavily if you don't catch all of the trig identities, but kind of do your best to make them look as simple as you possibly can. Think of it as a mathematical challenge. All right, there are also a whole bunch of equations that have pretty nice forms in polar coordinates and either don't have good forms at all or at least not as convenient a form in rectangular. So many of these we won't even ever look at the rectangular forms. we'll just look at the polar forms. These certain special forms that arise in polar graphing are helpful to recognize and be familiar with. I kind of say this is analogous to the idea that when you're graphing in rectangular coordinates, which you're all very familiar with at this point, if somebody says to you, the equation y equals x squared, not one of you would have to go grab a calculator to get a picture in your head, right? You know exactly what that parabola would look like. If somebody says to you, oh, the equation y equals 2x plus 3, you know immediately that's a straight line, slope of 2, y-intercept of 3. There's a whole bunch of equations like that, right? Y equals the square root of x. You know what that looks like. Y equals e to the x. You know what that looks like. All of those graphs you've become familiar with because you've studied graphs in rectangular coordinates for a long time. Of course, we're just now beginning to look at graphs in polar coordinates. So although I do say it is really helpful to recognize and be familiar with these, I also recognize that's not going to happen overnight. So what we're going to do is we're going to take a look at these, and we're going to take a look at how we can use the calculator to help us graph them. And then the more of them you do, the more you'll begin to recognize them, even without a calculator graph, just like you now do for rectangular coordinates. So let's take a look at a few different categories of polar graphs. First of all here, we have circles. We've already looked at circles centered at the origin. These are circles that have centers on either the x-axis or the y-axis. Notice here we've got a circle with a center right here on the x-axis. Here we've got a circle with a center on the y-axis. The equations of these circles are either r equals a cosine theta, those will have center on the x-axis, or r equals a sine theta. Those will have center on the y-axis. A here, notice, is actually the diameter of the circle. Let's try graphing a couple of examples of this in polar coordinates on the calculator. First thing you're going to do is go back to your mode key. Right? And we've used function mode most of our mathematical lives. We were using parametric mode in 10.1. We're now going to use this third one, polar mode. So you've now this semester used all 4 modes of functions on your calculator. So set yourself into polar mode. And now when you go to y equals, notice automatically you're given the form r equals instead of y equals. So I'm going to graph 2 examples. Let's first graph r equals 5 cosine theta. Based on this, cosine should have its center on the x-axis with a diameter of 5. Let's try it out. All right, well, kind of, sort of, but I can't see enough. I'm going to go with a zoom square on this so circles look like circles. Still no good. Let's zoom out. There we go, much better. By the way, after you hit zoom out, I had to hit enter to get it to actually do it. There's my circle, and notice 1, 2, 3, 4, 5 is indeed the diameter. Centers on the x-axis. So that one seems to check out. By the way, one more thing about this. I guess it happened to be set like this. Very often we've seen to draw a circle, we've had to go all the way from 0 to 2 pi. This circle I was able to draw with my thetas going just from 0 to 1 pi. So just something to kind of note and watch out for. Let's go back to our r equals, and let's do another one. I'm going to do a sine one. Let's do r equals, let's go with 2 sine theta. By the way, I probably should have said this a bit ago, but make sure your calculator's in radian mode when you do these. All right, it's pretty tiny, but I can see it, right? It is up and down here. The center is on the y-axis, and it looks like the diameter is 2. If I wanted to zoom in, you'll have to hit enter when you get back to the screen. I can see it a little bit easier. Yes, 1, 2 is the diameter, and the center is on the y-axis this time. Once again, in my window settings, my thetas were only going from 0 to 1 pi, and that did give me the whole circle. All right, let's look at the next batch of equations. These are called the Limisons and the cardioids. All of their equations have these forms. They're all a constant a plus or minus a multiplier b times either cosine theta or sine theta. All of the graphs in the examples here all use a plus b cos theta. We'll do a little bit of experimenting to see what putting a minus sign in does, or what changing the cosine to the sine does. We'll see it's a little bit predictable based on what we saw above with the circles. All right, Limisons and cardioids, what are they? This is a limison with a loop, right? You got this little loop in it here. And this happens anytime a over b is less than 1. Or in other words, a is less than b. A cardioid happens when a over b equals 1, or in other words, when a equals b. Notice that instead of a loop, a cardioid just comes to a sharp point right here at the pole. Okay? Cardioid, cardio heart, right? Kind of sort of heart-shaped, although the heart's a bit rounded down here. Down here, we have the dimpled limison. It doesn't have a loop, and it doesn't come to a point at the origin. Instead, it just kind of has a little dimple or a little dent in it. This happens when the fraction a over b is between 1 and 2. And then finally, the convex limison, right? Instead of a real dimple or dent, it just kind of has sort of a flattened side to it. And this happens when the fraction a over b is greater than or equal to 2. So, let's try graphing a few examples. Let's see, I'm going to do one like this first, with the a less than the b, and I'll do one like they did this time. I'll do the a plus b cos theta. So let's do r equals 2 plus 5 cos theta. So my a is less than my b. I should get a limison. Whoops, pull that down for you, sorry. A is less than b. I should get a limison with an inner loop. Let's try it out. All right, I'm not seeing enough. Let's zoom out. I try not to put my own x and y values in these because of the fact that I want to keep it square so circles look like circles. All right, well, I didn't exactly get that. It might be my window. Remember how we were only going from 0 to 1 pi? I think that's the problem. Most graphs need to go from 0 to 2 pi. So let's see if that fixes it. There we go, much better. There is that limison with that inner loop. All right, let's try this time. I'm going to go for a cardioid this time. I'm going to go for an A equals B. And this time let's go with a minus. So let's go with, actually let's go 3. Let's go with 3 minus 3 cos theta. All right, there's the cardioid. Notice that it comes to that point right there at the pole. So it is a cardioid. What did the minus seem to do? Remember I told you all these were graphed as pluses? Do you see how putting the minus sign in there just reflected it across the y-axis? So it's a reflection across the vertical axis here is all that did. All right, let's try a couple of the ones like the ones down here. Let's see. I'd like to do a dimpled limison next. And I have to have the fraction a over b between 1 and 2. And I think this time I've done a couple cosines. Let's try a couple sines and see what that does to our graph. So let's do r equals 4 plus 3 sine theta. Notice my a over b would be 4 over 3. 4 over 3 is between 1 and 2. So I should be in this situation. Let's try it out. All right, it is a dimpled limison. Notice that there's a little dent here, but the point doesn't reach all the way to the pole. So it's not a cardioid, it's a dimpled limison. What did using sine do instead of cosine? Well, notice, instead of the dimple being on the horizontal axis, the dimple is on the vertical axis. Isn't that kind of reminiscent with what happened with our circles up at the top of the page? When we changed from cosine to sine, the center of the circle switched from the x-axis to the y, right? Same kind of thing you're seeing here. The dimple changes from the x-axis to the y when we go from a cosine to a sine. All right, the last one, the convex limison that just kind of has a flattened side. This happens when the fraction a over b is greater than or equal to 2. So I'm going to go with 4, and let's go with a minus this time. Oh, what do I need? Maybe a 2 sine theta? A over b, 4 over 2 is equal to 2, so that would qualify. And there we go. Notice instead of the flattened side being vertical, on mine the flattened side is horizontal. That's the change again from cosine to sine. But it is this convex limison, that's sort of a flattened side. So again, I'm not expecting you right off the bat to recognize these and be able to graph them immediately, but just kind of recognizing them, starting to name them in your head, you'll get more familiar with them as time goes on. 2 more sets, 2 more families of curves. The next one I always think are kind of fun, the rose curves. Kind of look like flowers, probably why they're called rose curves. We have a or r is equal to either a cosine n theta or a sine n theta for these. And the value of n actually changes these curves a little bit. The petals, how many petals or leaves, they're sometimes called, of the curve, does depend on the value of n. If n is odd, then n actually gives us the number of petals. Notice here, this is an n of 3, and we had 3 petals. This is an n of 5, and it has 5 petals. Okay. However, if n is even, we actually get 2n petals. This one was run with an n of 4, and notice there are 8 petals here. This one was run with an n of 2, and there's double the 2 or 4 petals. So the number of petals does depend on whether n is even or odd. One other thing, take a look at the length of those petals. Whatever the multiplier is, the a value, that actually gives you the length of each petal. Each petal ends a units from the pole. Here again, whatever a is, that's the length of every single one of those petals. Happens here as well. Length is the same in all petals. It's always a. Okay. We're going to take a look at that in kind of an interesting way in one of our, maybe both of our examples. So let's try a couple. I'll do one cosine one and one sine one. One even, one odd. Let's see, let's do r equals 4 cosine 7n. Because, 7 theta. Because n is odd, n actually gives us the number of petals. So I'm expecting 7 petals here. Let's try it out. Oh, I should say 2. 7 petals of length 4. All right. Oh, interesting. Okay. We can kind of see the 7 petals. I've got a couple of issues here. First of all, I think I saw that go around twice. It looked like it was going over itself. Let's see if we can do the same thing with just 1 pi. Yeah, I get all 7 petals with just 1 pi. So here, I wasn't making a point of it when we went around 0 to 2 pi, but here I am able to take my thetas, just 0 to pi, and it gives the whole curve. Secondly, this looks a little bit kind of jerky, doesn't it? It's a little bit hard to see. The way to fix a graph when it looks real jerky like that is to make your theta step a bit smaller. It'll graph slowly, but it will look better. My step is 0.05 right now. If I change that step to 0.01, it should improve the look of my graph, although my graph is going to go kind of slowly. You'll notice how you can really watch each petal forming here. But notice that the petals are more smooth and rounded. It's giving me a better picture. All right, so there's my 7-petaled rose curve. The petals should have a length 4, and they probably do. I'm just going to experiment for a second. Can I zoom in on this at all, or is it going to cut it off? Yeah, it's going to cut it off, isn't it? That's all right. We'll go back to the other. I'm going to zoom back out. All right, as we said, because of the multiplier of 4 here, these petals should have a length of 4. They probably do, although it's a little bit hard to tell for sure. Here's an interesting way to see that. Back in my y equals, I'm going to graph a second function. I'm going to also graph r equals 4. Okay? That's just a circle of radius 4, right? Simple, simple polar equation. Look what happens when you graph them both. Do you see how the tip of each petal just touches that circle? So in fact, yes, the length of the petals really is 4. Remember, I was only graphing from 0 to 5, or 0 to pi, I mean. That's why it only graphed half the circle. But it shows me what I wanted to see. The length of each petal is exactly 4. All right, let's try another one. This time I'm going to try a sine function, and I'll try an even multiplier. So let's go with r equals 5 sine, and I want an even number in here. I'm going to go with 4 theta. Because I have an even multiplier, I have to double that to get the number of petals. So I'm expecting 8 petals of length 5. Well, that's kind of interesting, isn't it? We only got 4 petals, but they don't even look symmetric. I wonder, remember how we had limited ourselves to 0 to pi? Do you think this one maybe needs to go all the way to 2 pi? Let's try it. And again, I've got my theta step size set to 0.01, so it's graphing pretty slowly, but it's giving me pretty nice rounded petals. And you'll notice now we are getting more petals this time. There we go. There's all 8 of them. So we did indeed get 8 petals. But isn't this interesting? It's still a rose curve. When you have an odd multiplier, we only had to go from 0 to pi. But it appears that if we have an even multiplier, our thetas are going to have to all the way go to 0 to 2 pi. Once again, we said that these petals should have a length of 5. A nice, easy way to see that would be to add the circle, r equals 5. And those petals should just touch that circle. And in fact, they do. You can see that each petal extends out to a length of exactly 5. So those are the rose curves. Last type or family of curves we're going to look at here today are the lemniscapes. Lemniscapes are typically solved for r squared rather than r. They'll either have the equation r squared equals a squared sine 2 theta or r squared equals a squared cosine 2 theta. And you can see in both cases the shape is the same. It's just that with the sine you get kind of this slanted one, and with the cosine you get a perfectly horizontal one. Kind of looks like an infinity sign, doesn't it? All right, we'll try one of each. Let's try r squared equals 4 sine 2 theta. And we should get that type of lemniscate, and we should get, notice, the length of the loop should be a. In this case, a squared is 4, so a is actually 2. So the loop length should be 2. Now, here's the problem. The calculator will only solve, or will only graph r equals. It won't graph r squared. So what I'm going to have to do here is say r would actually be plus or minus the square root of 4 sine 2 theta. So I'm going to have to graph both the positive square root of 4 sine 2 theta and the negative square root of 4 sine 2 theta. By graphing both of them, I should get the whole picture. And you can start to see it is on the slant, right? It's really tiny because I've got a pretty small window in here. But we can zoom in if we want to. I'm actually going to do two things. Well, it's not bad. Let's go ahead and just zoom in. Still graphing. Looks like it's going around twice. Did you see how it kind of darkened down? I'm going to do two things. I'm thinking maybe I can get away with just 0 to pi. So I'm going to change my window that way. And then I'm also going to zoom in. So let's do the window. Let's just go to 1 pi here and see if we still get the graph. I'm going to go to a step size of 0.05. I think that'll be good enough, and it'll graph a little faster. Yeah, it's still a pretty good graph. And let's try zooming in on this one. It's pretty tiny. There we go, much better. And you can definitely see this. Just because these things are quite flat along the axes, it almost looks like it blends in right along the axis. But it is this picture. It is a lemniscate. Right? And we do get the whole thing when we just let our theta go from 0 to pi. All right, let's just do one cosine one as our last example for this section. Let's graph r squared. Make this one bigger. Let's go with, I don't know, 25 cos 2 theta. So in this case, my a squared is 25, meaning a is 5. This one should have a loop length of 5. Same idea. I'm going to have to graph r, so I'm going to have to go with the positive and negative square root of that. So the positive square root of 25 cos 2 theta and the negative square root of 25 cos 2 theta. All right, definitely need to zoom out. And this is kind of an issue with the calculator. It kind of misses some points in there. They do exist. This is one where the calculator just doesn't do that great a job of graphing this. So you kind of have to fill in a few of the missing points with your imagination. But I'm going to show you, even if I changed my window, so this was 2 pi, it actually doesn't get any better. Right? It still seems to miss those missing points. I don't know exactly why. Maybe it gets a little bit closer. So maybe I guess it does get better. Looks like maybe we do need to use the 2 pi. That was my mistake on that. It's probably the same for both of them, so I do apologize. We probably do need to give the whole 2 pi to get the entire thing. All right, so those are our Lemniscapes. And that brings us to the end of section 10.2.